Good morning, everyone. Guten Morgen. Hello, wie geht's? We're starting off now with a round of presentations in the AI Society booth. It's the blue circly thing right about here. I want to thank AI Society for inviting lots of fun speakers after me, but also me to tell you about these projects that are going on here. Me personally, my name is Ben Wolf. I'm from the Netherlands, quite close by. I speak a little bit of German, but I'm going to keep it English today. And what I want to talk to you today about is our project called SeaClear. And SeaClear is a project that aims to, well, search, identify, and basically get litter out of our oceans and waterways. And already on the first slide, you see our technical solution to do this. So we have two underwater drones that you can see here. These are the yellow ones, right? We have a flying drone up there from DJI, and we have our custom mothership, if you will, which controls everything. And the goal is to develop a whole autonomous system that you deploy on a site, let detect and search the trash and get it out if possible. Now, to start off a project like this, we are a Horizon 2020 funded project. We have university partners and we have partners in industry, such as the one we see here as well. And we started out with defining two use cases to get trash out of the waterways. One was quite easy to do because we have a partner in Croatia. The water is crystal clear. Game of Thrones was recorded there, so there's plenty of reasons to go there and to collect trash. A very important side note for collecting trash in that area is that most of the areas that you go to are protected. So you can only pick up the trash, you have to leave the crabs and the seagrass alone. So that poses a very challenging task to really classify the trash correctly and not touch anything else. The other extreme is a collaboration with the Hamburg Port Authority, where in the ports there's a lot of turbidity, the water is very murky, so it's very challenging to even see underwater, let alone grab stuff. And so today I'm going to show you how we're trying to tackle both of these cases. Another thing I am forgetting is with a lot of moving parts comes a lot of partners. So these yellow robots you see are developed by a company in Marseille, Subsea Tech, who is one of our partners as well. And the goal is to make this whole thing autonomous. So it has to decide for itself where to go. And there are some advantages in that as well. So the hidden problem that we're trying to solve is the plastic soup, or as we call it, the plastic sediment, really, because only 5% of the trash is on the sea surface, but most of the trash is in the water columns below or even on the sea floor. And that's fine and dandy if you're a diver and want to do a beach cleanup. But if you want to pick up trash 10, 20, 100 meters below the surface level, you cannot get divers down there. You can get diver bells or very experienced divers, but they become very expensive very fast. Of course, I would like to tell you the story that we don't need this, but at the current rate we're going, in 2050 we will have as much plastic by weight in the oceans as fish. And I'd rather have some fish than plastic in my mouth. I'm not sure about you guys, but I am. Here we see one of the images that I should have played earlier. But this is what we encounter in Marseille. So we have trucks on the floor, pieces of cement, or consumer plastics, and we want to get rid of those. Now the better thing to do, of course, is to recycle, not have the plastic at all, get rid of packaging, but that's not within our control. We can promote, of course, a circular economy, so make sure you recycle more, and do stuff like, so in the Netherlands, we don't really collect tin cans, they're just with the trash, but we're copying Germany and we're mimicking that now, but we need solutions that really solve the problems that we have caused in the past. One way to do this is beach cleanup actions that are happening in Croatia as well, and which is actually the inspiration for this technology solution to be developed, because you cannot be reliant on volunteers to clean the beaches every time, or reliant on these divers. And also, I don't know if you've heard about the ocean cleanup, but that's a project also originated from the University of Delft, where you clean the surface, which is only 5% of the waste. It's still a huge task, but it's not enough. So if you want to go underwater, you basically only have divers or robots. And I'm going to try and convince you that robots is the way to go. I mean, we're at a fair here. So one thing is the cost of getting material out of the water. So in shallow areas, divers are fine. They're very cost effective. They're happy as well because they can see and it's warm. But if you go deeper, it will become uncomfortable for divers, but also more dangerous. The time that they can stay underwater is reduced, and also like for an hour mission, they can only maybe spend 10 minutes grabbing material. So it becomes a longer mission, more expensive and more dangerous. So we don't want this, especially if you think about the kinds of trash you can detect on the water. If it's just a bicycle tire or some broken glass, that's fine. But if you find unexploded bombs or whatever, you really don't want stuff near human lives. And add to that, if you have very aggressive high and low tides as well, you don't want to subject our divers to that. The robots, I mean, if they fail, it hurts my heart, but it's fine. It's just a robot, right? So I want to argue that it is a cost-effective solution to get robots here, but also it's a lot easier on the conscience to have robots doing this kind of dangerous jobs while helping us to clean the ocean. So here is an animation that may or may not play. It will. Here we see an animation of how this system is going to work in process. The only difference is the water that we are seeing in real life is way murkier than this. But so we search and identify the litter, and the idea is that we have an app or just a website where you can request a deployment. We will drive our SeaCat, our surface vessel there, and it detaches itself, it detaches all the other robots with tethers and comes up with a plan to map out the area. So we start out with a 3D map of the ocean floor and then get our smaller robots in to do the detailed groundwork. So we have this observation robot that does a detailed scan and maps on the ocean floor where the pieces of litter are and whether they can be picked up. This collection ROV that you're seeing here can pick up objects up until about 7 kilos. So the cans or the beer bottles, that's fine. We can pick that up directly. But if it's larger, let's say a forsaken bicycle or a chair, then we just map them on a cart and just hand them back to the end user and say, okay, you need a dredger for this, or maybe you need a more specialized crew. But whatever we can pick up now, we pick up now. And the idea is to deposit one of these collection baskets periodically. And as I think it's currently configured, we can do an area of 300 by 300 meters with one collection basket, where it will take about 3 hours to forage the whole area, make the map, and collect the litter that we can pick up, depending on the things we've seen in Croatia. Granted, Croatia is quite a clean seafloor, so in industrial areas like Marseille or in ports, it may take a little while longer, but we're going to get the trash out for sure. Oh, the thing I didn't touch on is the drone. The drone we use when weather conditions are nice. To take pictures of the surface litter, because sometimes wherever the surface litter flows, you can also bet there's underwater litter flowing in that same direction. So that's how we might figure out where do we want to start looking for trash on the water. And if nothing else, it serves as an anchor point for figuring out where everything is. Because above ground we have GPS, right? Google knows where this phone is. But as soon as you go underwater, these signals are lost. So we have our mothership that has a sort of underwater GPS, USBL, that can at least detect large objects, but also can detect the drones that we have in our area. So at least relative to the mothership, we know where the other robots are. And then on the mothership, we have GPS, or with help from the drone, if they can see our robots, to get a full picture to make sure that if we find some trash, that we know exactly where it is. And we're not like 10 meters off to the left, because then there's no use of making a map. So these are the two sites we've already visited. We're going to, so we went to Dubrovnik last year, and this spring we went to the port in Hamburg to do our deployments. In Dubrovnik, we were on manual control just to test out the systems, and in Hamburg we went half autonomous. Only half autonomous because the mothership was autonomous, but the drone saw nothing. It's very murky on the water, so instead of our camera sensors, we had to rely on sonar vision. And sonar vision is kind of tricky. We're trying to tackle that as well with AI to really detect objects, but currently we only trusted our skilled operator to move the drone about. The goal for this year is to go after the summer to Marseille, to do a full autonomous test in clear water, and then come back to Hamburg, to the worst case scenario, and show that we can deploy everything autonomously and hopefully pick up some trash in the process. So the challenges in terms of a robotic standpoint are, how do we move things underwater? And I'm not an expert on this. Stefan, the guy who couldn't make it today, is an expert on this, but how I see it, because we have these robots that are tethered to our mothership, we have tension on these ROVs, we don't see very well underwater, and you have to figure out, if I move the thrusters this much, how far has my robot actually moved, right? And even if you figured out like a model of movement for that, you cannot really trust on it, because if you're grabbing objects, then you have this grabber underneath that changes your center of gravity. And if you pick up objects, if it's a very light object, you might be fine. But if you pick up a rock of 6 kilos or a piece of trash, that will change how you move. So we're incorporating camera vision and sonar vision as well in this grabber ROVs to make sure that we are where we think we are. Another challenge we face is the limited resources. So on the mothership, we have a big battery, but also a generator in case we need more power. But it's also a question of, how do we communicate everything? How do we make sure that the end user gets snappy feedback? Because while the mothership has a great internet connection to stream camera feeds or detection feeds or sonar feeds off-site, everything still has to go to an undersea cable. So that's why we are doing some of the detection on the robot itself, so that in case connection gets lost, can still maneuver to safe places, but the bulk work, like the machine vision and the AI, we tend to do on the mothership. That's our current solution, and we might shift in the future, who knows. And the biggest challenge, the challenge I face every day, is trying to make the darn thing see underwater, because this is what we're dealing with. It's always blue, it's very pretty, but it's not very clear, SeaClear, what we see under there. And so we give our cameras a little bit of an edge, or at least we try to, by both combining the data we have and trying to improve the quality of our data. So in our case, we have sonars, right, for these ROVs, and we have camera systems, and we combine that with the mothership that has this 3D map underwater. So that helps with the localization, but that still means that the quality of the camera images are not great. And we want to go into a situation like this, where for every object we have, we detect a bounding box, and with 100% accuracy, we can say what it is. But it's not as easy as taking a picture and drawing a box. Here it is, but not in real life. In real life, we want the robots to operate themselves, and when they think they find an object, we do something that's called active sensing, where the robot gets closer or takes different views to really make sure this is a soda can and it's not just a piece of plant. Or what's really hard is green beer bottles on the water. Darn you, Heineken. Because green is normally a color of nature, but you really have to make sure that you're picking up a beer bottle instead of the plants that you were sworn to protect. And this is one way where I am focusing on making the computer vision systems easier. So computer vision systems, you've seen them all around. There's a camera, they detect a person or whatever. They work extremely well because there's lots of data of above water images. For underwater images, there's not a lot. So we're trying to remove the watercolor, if you will, and trying to make it a little bit more easy for the camera to spot things. Here, for instance, I can see the little debris on your right. A little bit easier in the corrected picture, that's a little bit brown, versus the uncorrected picture, which is blue. And on the next slide, I will show you what the end user sees if we don't correct the image or whether we do correct the image. And spoiler alert, if we do correct the image, we cannot send the corrected image over because it takes a long time to process. But on that version, we do actually see some detections coming through. And that's with the added help of trying to remove the watercolor, do the detection, and then send those detections, which are, in this case, just the green patches or the blue patches, back to the end user. And so I was very happy that at least some of these efforts worked. But it's not enough. And that's why within this project, one of the main goals is as well to gather more data of underwater objects and label them correctly and send them out to the world so that not just a bunch of researchers have access to it, but more universities around the world or research partners can develop more and better algorithms for detecting stuff underwater, because it's a big problem and we're not going to solve it alone. And people are hungry for this type of data. I mean, everybody's hungry for data, but this is exceptionally rare. Here's another example from a movie still. Like, I cannot see anything in the green. It looks pretty, but after correction, we can actually detect here, I think this is a cement tube, which is labeled as a sports ball, don't mind that. But even here, if the human operator with some latency can see, hey, you missed some objects, you could steer the deployment back that other way and say, okay, I did see a branch here, and in that way it is actively training the system to add these things into its detection algorithm. Or so we hope. Another thing here is, look over there. What do you see? I see nothing. This is what we see in the Hamburg port. And we do see some stuff in the sonar images. And here is where we want to try do sensor fusion. And we have also a nicer example of Dubrovnik. In that port of Marseille, Subsea Tech, where we do see both tires and a chair, both in sonar and in camera images. And by having a model, so having a piece of software that can detect both in both places, we try to inform the sonar images as well. So hopefully in this case next year when we're back in Hamburg, we can feed these sonar images to our camera detection system and say there should be something there. Take a closer look, take another angle, and hopefully see through that murky water and actually detect the objects that we want. So after we found all this trash, we need to map it, especially like these larger things like cement tubes, like chairs, the things we cannot catch with our gripper, which you can see there, by the way, after the talk. We have to present them in a 3D map, and this is going back to the end user. We can have two modes of operation. So either we only scan and we just say, okay, this is the scan, do with it what you want, or we can also select our collection ROV to do that as well. But collecting the trash takes a little bit more time. So this is where a choice can be made, and this could be one of our end products as well. Now the final part is where I am a little bit less experienced, but this is about how we control the robot. How do we make sure where it goes? So a naive approach would be see the detections of the things you want to protect and see the detection of the things you want to grasp, in this case the Pepsi can on the floor, and plan a path accordingly. The thing is, we did not detect the rock over here. So at some point it will hit it and mission is over. So that's why we're also trying to develop robust models for movement. In this case, that will incorporate a skid underneath with the gripper and changing conditions and try to be robust to the situation. This is the latest challenge we're working on. We're not done, but we're very excited to see where it goes. Thank you all for your attention, and have a great rest of the day. While I'm here, if you have any questions, feel free to ask, and otherwise I'll just be pulled off stage. If nothing else, you can visit me in the booth right over there in the environment corner. Come and say hi, and yeah, see you around.